Okay, let's look at some log properties so we can do some function manipulation. All right, so since they can also be written in exponential form, the same properties apply to exponents that can be applied to expressions involving logs. All right, so hopefully you remember some of these. If not, we're reviewing them here. Your product property, this allows if you have the log of a product, x times y, it can be separated into log of x plus log of y, all having the same base. I'm just not saying base b on each one. That's the same as if you have two quantities being multiplied with like bases, you would add the exponents. That's what's happening here. If you have log base b of division of x divided by y, it can be broken up into log base b of x minus log base b of y. And then last one, your power property. So all these are the same as your exponent rules. Log base b of x to the n, it ends up being n times log base b of x. All right, so you can see them all used there and as an example. We can do the same thing that we did with exponential functions and be able to write log functions in different forms using these properties and then look at transformations that are happening. So we are going to be condensing each to a single logarithm. So the first thing I always look for are coefficients. I know that those would end up being exponents. So this would be log base 2 of x cubed. Then, because we have two logs being subtracted, it's really log base 2 of their quotient, x to the third over y. And you should put it in parentheses because now it's in a large quantity that we're taking the log of. All right, for b, we've got some coefficients. So they will be exponents. So a squared, b to the fifth, and that's still this log base 7 of 4. And now when we put it all together, we've got 2 that are being added. So they're going to get multiplied. And then because it's minus the log base 7 b to the fifth, that will be what we're dividing by. All right, no coefficients on any of these, so we don't have any exponents. Now, because these are all being subtracted, we've got x over, and then these two, because you can rewrite it as factor out the -1, then it'd be log 5 plus log z. Those two get multiplied, but in the denominator. Okay. Another way to think about it is you would end up with log of x divided by 5 divided by z. And since that's a complex fraction, that would be the same as multiplying by the reciprocal, which would again get that z in the denominator with the 5. Okay. So to me, I like to just factor out the negative, and then I know they're both being multiplied, but in the denominator. But you can deal with the complex fraction if that's what you would prefer. All right, we got lots of coefficients on this one. So 2, a 3, and a 1/3. So the ab squared gets squared minus log base 3 of c cubed plus log base 3 of d to the 1/3. Okay, so now this middle one's the only one being subtracted, so that's what's going to go in the denominator. The other two get multiplied up top. Now, we can deal with these different ways. I would probably square that whole thing, so make it a squared b to the 4th. And then you can leave this as d to the 1/3, or we could write it as the cubed root of d. All right, this would usually show up multiple choice type questions, so you would look for one variation of them. Okay, but recognize, d could be d to the 1/3 or the cubed root of d. All right, now this last one's a little different, right? Because we don't have a log on this too. So let's go back and think about what could we express log base 6 of something and have it equal to 2. So that means 2 is the exponent on base 6 that gives us 36. So that in itself is equal to the 2. And now since we have logs with the same base, I can put this together as log base 6 of, and then their product, 36x. That one got a little tricky, but it's just using how logs are evaluated. All right, these are going the opposite direction, so we are going to expand them using our log properties. So this first one I see multiplication, so I can do log base 2 of 8 plus log base 2 of x cubed. And then because of the exponent, that can come down in front. So we can go log base 2 of 8 plus 3 log base 2 of x. Ooh, this is a good one. So first thing I'm going to do is rewrite that as that whole thing to the 1/2 instead of that radical. So the 1/2 can come down in front. And I'm just going to put big sets of parentheses. And then I can break this up. It would be log 10 plus log x minus log y squared. And then because of that y squared, we can make it 2 log y. You could distribute the 1/2 all the way through, but I'd rather condense it down and leave it out in front. All right, and then for C, all right, so we've got division, so let's break that up. This would be x minus 4 to the 3rd minus log base 5 of y to the 5th. Now, since it's all down there, I'm going to do plus log base 5 of z, but in parentheses with the subtraction. All right, and then I would like to deal with both of these exponents. So 3 log base 5 of x minus 4 to the 3rd minus 5 log base 5 of y plus log base 5 of z. And again, you could distribute the negative and just go minus minus there, or I prefer the parentheses because to me, visually, that means those two are down in the denominator together being multiplied. All right, so here we've got a function given to us, log of 100x is a horizontal dilation of g of x equals log x, right? It's horizontal because in here we're multiplying by 100, so that would be a horizontal shrink by 1/100. All right, we want to show that it can also be written as a vertical translation of g in this form. So let's use some properties. Because we have log of a product, we can break it up into the sum of the two logs. And let's recognize here that log 100 is really base 10. So 10 to what power is 100? That's 2. So f of x, I'm just going to rearrange that, is log base x plus 2. So we've got it in this form. G of x is log of x, plus 2 would be the k. So really, this could be a vertical shift up 2 of g of x. All right, looking down here, we got the change of base property. All right, so with the change of base property, we can also rewrite logs in a different form. So if you have log base b of x, another way to break it up is use a different base and do log base a new base of x, which is what you were taking the log of, divided by log base a, same base here, of your original base b. Okay, and this works when a is not 1 and greater than 0. So this actually shows us that all log functions are actually vertical dilations of each other. So let's look at what that means. If we're given f of x is log base 4 of x, and g of x is log base 9 of x. Show that f is a vertical dilation of g by finding the value of k such that f equals k times log, or k times g of x. So let's use our change of base property to rewrite f of x. So it's a log base 4 of x. That means we can use any base we want, and we would do log whatever base of x over log whatever base of 4. And since we've got g of x that's a base 9, let's use base 9 for both of them. It wouldn't matter the base. It could be base 10, it could be ln, it could be any base you'd like. All right, so now if we look at this, it's really 1 over log base 9 of 4 times log base 9 of x, which is your g of x. So f of x is a vertical dilation of 1 over log base 9 of 4 on g of x. Not something you're always going to have to do, but being able to recognize it and being able to use your change of base property when necessary is helpful. All right, now something we talked about before, remember that your logarithm with base e is called your natural logarithm. All these properties hold true up here. Okay, so the properties that we've already looked at in this lesson. So if we're given e to the n equals 2x to the third, convert the above to its equivalent log equation. All right, so if we look, we can use this, e as our base. It would be log base e of 2x cubed equals n, because that was the side where the exponential was all by itself. This is the same as natural log of 2x to the third equals n. So that's all we converted it. And then part B, using our properties, I was getting ahead of myself there. Using our properties, expand it to write n as the sum or difference of logs. So n, if I break this up, it would be ln of 2 plus the natural log of x cubed. And then because we have that cubed in there, it's the natural log of 2 plus 3 natural log of x. So those same properties hold true no matter what the base of your log is. If it's just log, log base e, log base any other number.